Hi, my name is Jack, and my indie lab was on spectrophotometry. Originally, the purpose of the lab was to demonstrate the effects of color filtration on percent transmission. Basically, I was going to take a glass prism, or better known as a monochromator, to separate white light into the full color spectrum, and then I would transmit that through a color filter, plastic color filters. So I had one for each color of the known spectrum, and like red, yellow, blue, green, the colors of the rainbow. And I was going to see that the exit intensity and compare it to the initial intensity of the light for each color made by the monochromator, and see if there were any linear relationships. And I did that, but I replaced the monochromator and the light intensity sensor that I was going to use with a spectrophotometer, which is basically a little black box that does everything that I would have been previously doing, just more accurately, and it's a lot easier to set up. But because I did that, I drastically shortened my lab, and I needed to add more parts, so I added in color addition, as well as the primary and secondary colors of light. The primary colors of light are red, green, and blue, and the secondary colors of light are cyan, yellow, and magenta. You might think that the primary colors are red, yellow, blue, which is what you've been taught in art class, most of you, but that's just because they're the common colors used for paint mixing. But in light, red, green, and blue are what's used to, you can like add them together in different proportions to make any other color. So for part one, I said that for each color, that particular wavelength in the spectrum would have the highest percent transmission. So basically, if I was shining light through a yellow filter, then the yellow portion of light that I was shining through that yellow filter would have the highest percent transmission through that filter. And then as the wavelength gets smaller or larger values, so as the color changed away from yellow, then the percent transmission would get lower. So essentially I was saying that there was going to be one peak, and then it would make like a parabolic formation. And then part two is where I was adding two primary color filters together to make secondary color filters. I didn't talk about that yet, but basically by adding two primary colors of light together, you get a secondary color of light, which is magenta, cyan, or yellow. So I said that I could do that. And then part three is that I thought that although it will be possible to create a shade of indigo, there will be a high error when compared with an indigo filter graph. Basically, I was trying to create one color from the spectrum using other colors to talk about color addition better than just secondary and primary colors of light. So I was making indigo, and I said that there was going to be high error basically because I was adding two filters, and in a second. Equipment, spectrophotometer, the filters that I made, I cut them out from the sort of things found in the back room. 3 secondary color filters, Logger Pro interface, laptop with Logger Pro installed. Here's my diagram. Background. So I said violet equals purple because usually in the spectrum, violet is substituted for purple, etc. So if anybody was confused, purple's purple. Transmittance equals T, A equals absorption, I initial equals the intensity of the light before it enters and passes through the median, which in this case was a filter, and then I final was intensity after passing through the filter, and transmittance can be calculated by dividing I final by I initial, and then percent transmissions is the final intensity divided by the log base, or log of 100. Here's a little background. So basically, colors are wavelengths of light. So we see wavelengths as colors. So here are the ranges of wavelengths at which we see certain colors. So if you see a wavelength of 670 or 680, you'll be seeing red light. And I needed to take these medians. I took the middle number from each of these wavelength ranges to find a way that I could do error analysis on my labs to analyze a spectrophotometer graph, you basically just have, it's not really linear, you can't really get data points, or you can get data points, but you don't know where to go, so I was getting a data point for each specific color of the spectrum. And I talk about that here. Basically, you can take percent transmittance intensity and absorbance from one spectrophotometer graph. You can just convert it. Specific things. So here are my graphs. Part one is I just took graphs of each single color filter from the spectrum, and I've given an example graph here. So this is the red filter. As you can see, it reached its peak around wavelengths of between 600 and like 800, showing that the red was most transmitted through there, while it was really low around the violet and blue areas of the graph. Then here's part two, where I was making secondary colors. So blue and green make cyan, and as you can see, I added blue and green filters, and I also just had a lone cyan filter, and the graphs are very similar, except the peak transmittance around cyan was a little bit higher in the single filter graph, and that's because basically with two filters, it would be double as thick, and so as light is passing through those two filters, it'll get caught up more because there's more distance for the light to pass through, but it's making the same color. So I did that. And then here's my indigo thing. It's the same concept. I had a higher transmittance through the indigo single filter than through the blue and violet filter combination to make indigo. My data tables, so, I'm gonna go back. I didn't go back. I'm just gonna.
You have 1 minute. Jack, 1 minute.
Oh, okay. So for each color, I took the value of the median range and I put those into my data tables. So here is the percent transmissions for each of those wavelengths. And that's how I was getting data, like concrete numbers from my graphs. And those happened for each of them. Then I went around to error analysis. So I only did error analysis for parts 2 and 3 because there was no real way for me to do it for part 1 unless I had like an ideal like filter. But for part 2 and 3, I got very low error in the first ones where the peaks were, but I got very higher down where it was very low because the accepted and experimental values were very similar. Conclusions, primary lights can be added together to make secondary, as well as you can create any color of the spectrum via primary light addition. Thank you.
We have time for just one question.
Ben.
Your graphs of transmittance versus wavelength, I was curious because you said that you used a red filter, and yet in your wavelengths in the red spectrum that had the highest transmittance, if that filter actually looked red and transmittance is proportional to absorption, that should be the reverse, where it reflects almost all of the red light.
No, it transmitted most red light. Also, if you notice my graphs, like there's some green light and yellow light that are transmitted through. That's because the colors weren't exactly at those wavelengths. Like the color of my red filter was a little bit darker, so it had like some green light in it. Yeah.
No, but like if you're looking at something red, it's because it reflects red light.
Mm-hmm.
Right. So transmittance is how much light is absorbed by the object, essentially, like more or less.
No, not in terms of a filter. Because a filter isn't reflecting light, it's letting light through.
Yeah, it's how much light is getting through.
So
the percent of the light of that wavelength got
So
through
there
the red
should,
filter.
there should still be almost no light getting through of that color if it's reflecting it.
But it's not reflecting.
It's not, it's passing through.
Wait, is the filter red color?
So what I'm saying is then it shouldn't look red.
No, because it filters out the not red light. So if you look through it at something, the red light is coming
The
into
purpose of
your
a filter
eyes.
is that it doesn't reflect anything. You're right, if that filter was reflecting light, it would seem everything but red.
It would look like a mirror, kind of, or like a wall.
Yes.
Jack, we really have a great question here, and it shows that there are some things that are really confusing about this. Can you help us to understand the 3 things that might happen when light hits an object? What are the 3 things that light could do when it hits an object?
Reflected, absorbed, or transmitted.
Okay.
So you can, the spectrophotometer takes all this data, and I said in my background how to convert between it. So basically, it just takes the intensity and the initial intensity and the final intensity, and you can convert between the 3.
Thank you.
You can compare it to the initial intensity of the light for each color made by the monochromator, and see if there were any linear relationships. And I did that, but I replaced plastic color filters. So I had one for each color of the known spectrum, and like red, yellow, blue, green, the colors of the rainbow. And I was going to see that the exit intensity. Basically, I was going to take a glass prism, or better known as a monochromator, to separate white light into the full color spectrum, and then I would transmit that through a color filter. The monochromator and the light intensity sensor that I was going to use with a spectrophotometer, which is basically a little black box that does everything that I would. Hi, my name is Jack, and my Indy lab was on spectrophotometry. Originally, the purpose of the lab was to demonstrate the effects of color filtration on percent transmission,